Now we're getting to the guts of it, pulling it all together. We're going to look at how stock assessment models work. But before doing that, let's just reinforce one very important point, and it goes to the central question of why do we use stock assessments? What's the point of them? Well, the main reason to use stock assessments is that scientists can't directly count all the fish in a stock, and as a result, they need as much information as they can get to estimate how much fish can be sustainably harvested. This information includes length, age, catch, discard and catch rate information collected every year, combined with what is known about stock recruitment, growth rates, maturity, reproduction and mortality. There is simply no way anyone can analyse this amount of information in their head. So, scientists plug all this information into a computer model that's customised for each species. From this, they work out how the stock is responding to fishing pressure and provide a prediction of what catches can be sustainably taken in the future. Remember, weather forecasts aren't always right, but they're still much better than not having a forecast at all. Let's go back to our diagram and see how it all fits together and how a model might work. First, let's recap on the variables we've already discussed that go into the model. Reproduction and recruitment were first, and they tell us how many new fish are entering the fishery. Up next was age and growth, which tells us how quickly fish grow, how many fish of each age there are, and what age reproduction begins. Mortality rates were the next cab off the rank, with natural mortality and fishing mortality estimated from age and growth data. Logbook and observer data also helped with the estimation of fishing mortality. Availability and gear selectivity were next, and they work across the whole diagram because they affect how we interpret and adjust much of the other data collected to better represent the entire population. Finally, commercial catch per unit effort, CPUE data, and fishery independent surveys inform us about abundance and population change, whether the stocks are going up, down or remaining steady. So, now we've collected all this information, let's see how all this goes into our stock assessment model. We could pretend that in this section we'll be able to explain everything about how stock assessment models work. The truth though is that they're bloody complex, and only specialised scientists actually fully understand all the details. So instead in this section, we're going to treat it a bit like a black box. That is, feed the information in, press the go button and get the results. But we'll also have a little peek inside the black box to look at how it works and how small adjustments in the way scientists use and interpret the data can affect the results. Let's go back to our diagram and start with the factors that increase population size: recruitment and growth. We'll start with recruitment. Because of availability and trawl net selectivity, tiger flathead are recruited to the fishery at about 25 centimetres length, or 3 years old, and this is when we start measuring them to get information about the stock. Flathead of 3 years and older are represented here by the green bars. We know from length measurements and ageing data that the age frequency of the tiger flathead population looks something like this. We also know that the tiger flathead mature at about 4 years old. Putting this together, we can see here in 2005 the proportion of the fish stock available for breeding. This is called the mature or spawning stock biomass. A good way to demonstrate the relationship between spawning stock biomass and recruits is to show age frequency graphs for a number of years. The number of fish spawned by the spawning stock biomass is estimated in the following year, 2006, represented here. The point is that biomass of these very young fish are estimates because they're not caught by the fishermen. The model estimates their biomass based on the spawning stock biomass from the year before. Moving into 2007, our year 0 fish are now 1 year old, and we have a new population of year 0 fish. As you can see, we've lost a few of the year 0 population through natural mortality. Moving into 2008, our original year 0 fish are now 2 years old and getting close to becoming recruits, and As would be expected, all the others have moved on a year and we have a new Year Zero population. Now into 2009, and much to their proud parents' delight, our Year Zero fish have graduated into the fishery. The point here is that recruitment levels are usually dependent on spawning stock biomass, and the recruits we see in 2009 were produced by the spawning stock biomass of 2005. If the spawning stock biomass in 2005 had been bigger, then we might have seen more recruits. If it had been smaller, we'd have seen less recruits. Recruitment is naturally variable because of the high mortalities that the eggs and larval fish can suffer. Remember that when it comes to stock assessment models and commercial fishing, we aren't interested in fish populations, but the biomass of the stock. So the other factor, apart from recruitment, that leads to an increase in stock biomass is fish growth. From our VB curve, we know that on average, a 4-year-old tiger flathead will be 35 centimetres long, and at age 5, it will be 37 centimetres long. On average, a 37 centimetre tiger flathead will be heavier than a 35 centimetre tiger flathead. So, in addition to the year's recruitment, the model calculates weight increase due to the growth of fish already present to end up with a biomass for each year group and a total biomass for the stock. But we're getting a bit ahead of ourselves in estimating the total biomass for the stock. This is the most complicated part of the process, and the final step we'll look at in this section. So, factors that lead to an increase in the biomass of the tiger flathead stocks are recruitment and growth. Let's now look at the factors decreasing the stock biomass, mortality, both natural and fishing. We've previously discussed natural mortality, which is caused by things such as ageing, predation, disease and lack of food. These aren't calculated separately, but as a single variable. Fishing mortality is pretty easy to understand and to calculate. We know how much tiger flathead was caught from logbook records of landed catch. We know what size and age they were from our length frequency and otoliths, and we have estimates of how much was discarded from observer programs. Together, they account for fishing mortality. Combined, recruitment, growth and mortality each describe different factors that act to change the tiger flathead biomass each year. We've also talked about how catch rates or fisheries independent surveys show us how much the biomass changes each year. Now, pretty much all that's left to work out is how big the total biomass for the tiger flathead stock is and how much we can sustainably take. This is the hard bit. Estimating the biomass in each year is complicated, so without going into too much detail, we'll explain a few things. There's a couple of facts about a fish stock biomass that we already know. Firstly, it must be bigger than the annual catch. Now, this might seem obvious, but it's important information as it sets a minimum possible biomass for our fish stock. We also know that fish biomass is not endless, and that there is some limit that the ocean can handle. Biomass then is going to be somewhere in between, but working it out is a bit like the process of triangulation when navigating. Without a compass or a landmark and no GPS, you are lost at sea. With just a compass and one landmark, you might know roughly where you are, but you don't know your exact position because you don't know how far from the landmark you are. If you know the compass bearing of 2 landmarks, however, you can work out your approximate position. But if you are unsure about the landmarks or can't get a precise reading from the compass, then you are less certain about your position. By using more landmarks and improving the precision of your compass reading, you become more confident that you know your exact position. In a similar way, a stock assessment model is lost without any information. Also, the model can use more than one type of information at the same time to estimate the abundance of a fish population. The more information it gets, and the more precise that information is, the more certain you are in the estimations that come out of the model. By using all of the past and present information that scientists have on a fish population, the model can calculate the vital missing bit of information, stock abundance or biomass. The most important information that gets estimated by the model is the current biomass and the biomass before the fishery began, termed the virgin biomass. These are the critical numbers that feed into the harvest strategy that go to set the total allowable catches. We'll cover this in more detail in the final section. What's more, if you provide even further information to the model, you can also use the model to predict the biomass, recruitment, age structure and sustainable catch levels. Now, no one is saying that these model predictions are perfect, and the further out they predict, the more imprecise they get. But they are the best tool we have to make sense of all the information we've gathered. Remember, weather forecasts? They're not perfect, and they become less accurate the further out they predict. We still use them though, all important information that we can turn into a number or quantity that helps us to estimate the biomass should be used in the assessment model. That brings us to the end of the black box. Just to recap, in this section we combined all the different components of the stock assessment model and showed you how they work together. At this point you might be thinking, well, how does the model actually use all this information? How do we know the model works? How do you know that the results actually make sense? Well, it's called model fitting and sensitivity testing, and we'll talk about that in our next section, opening the black box.